Our program is divided in three different sections: the modules or libraries that represent programs that other people wrote, the data definitions, where we define the information that enters the algorithm, and the coding section, which is where we implement the algorithm. In the libraries, we'll simply use the pygame library and the math library. We will use math to incorporate the sign function. In the data definitions, we encounter first the hyperparameter res, which represents the dimensions, width, and height of each square. Dims is represented as a compound data type of type tuple that contains two integers that represent the number of columns and the number of rows that our grid will be made out of. The screen connects the dimensions of each of the tiles by the total number of tiles that we want per column and per row by multiplying these values together and therefore transforming such values into pixels. These ones are also integers. The display variable creates a screen for us by calling the method setMode from the display sublibrary and the pygame library. setMode receives a screen, which is a tuple that contains the width and the height of the screen. The data definition tile is the basic unit of information in our program. It contains as its constructor two parameters, the number of the column and the number of the row where this tile is located relative to its grid. We incorporate these parameters or attributes inside of the constructor, and we calculate the position in X and Y by simply taking the column and the row for X and Y respectively and multiplying it by the resolution. In line 21 we have the rect component, which is sometimes called the hitbox. Pygame's rect is the instance of a class that contains the position in X and the position in Y of the top left corner where that rectangle or square starts, and then moving to the right certain amount, which in this case is the constant res, and down the same amount because this is a square. The color will start as black. The helper function draw is in charge of using the draw sublibrary from the pygame library and the rect method, which takes the surface in which we want to render the pixels, the color that this square is going to have, and it takes the attributes from the rect component called self.rect in order to know the position and dimensions of the square that has to be drawn. Here's where things change relative to the previous algorithm with one dimension. The tile grid data definition is a compound data type represented as a list of lists. It is therefore a two-dimensional array of tiles. We will generate the tiles procedurally. We start by creating an empty list called tile grid. And for every single number between 0 and the total number of rows that we want in the grid, we will first create a tile row that is also an empty list, and then we will populate that row using a second for loop. Let's focus on this for loop right here, because it may feel the most familiar. For every single number of column that we want between 0 and the total number of columns we want in one row, we will do two things, which characterize procedural generation. Number one, create. We generate a tile that receives the two parameters C and R, which are integers, that are received by the constructor of this tile template. And once we create a tile, we append it. We put it inside of the tile row, which is locally created inside of every row that we generate. Once we are done, we add the entire tile row to the tile grid. This is a compound data type of type list, and that means that the best way to traverse that complex structure is with a for loop. The template starts with a for loop that goes through every single tile row in the tile grid. For every tile row in the tile grid, we do whatever we want, but we do it to the tile row. The tile row is also a list, and we apply the same logic by traversing that tile row using a for loop. This time, the loop variable is designated as tile, because that is what we call the elements that live inside of a tile row. The three dots will represent the action or function that will receive or consume the object we call the tile. Now that we have the basic elements in place, let's start the coding process. We will begin by creating a draw function and an update function. It's something that we will always do when working with pygame. These two functions are in charge of rendering pixels in the screen and updating the states of the elements that are involved in the animation. We are going to run these functions forever or until we finish the application by closing the window ourselves. We're going to use an infinite loop to do this. In the draw function, we follow 3 steps. First, we're going to change the background color by using the method fill that is inside of the compound object we call display, which is a pygame surface. I'm going to call this green because I want to make sure that I can see any color green as background. As a matter of fact, I'm interested on the opposite effect. If my grid is made properly, I should not see any green at all, because every space, every pixel in the screen is going to be covered by a pixel that belongs to a tile. We're going to add 3 dots in here. We're going to get back to it, and we are going to finish the draw function by calling for a handshake between Python and the programming language that is creating the screen. Remember, Python doesn't work asynchronously, so it has to rely on other programming languages in order to accomplish this. This line of code is simply calling for an update on the screen that second program produces. So what do we do here? I'm going to copy the template for the tile row, and I'm going to paste it here. I fix the tabulations, get rid of the comments, and the thing I want to do to each tile is to draw it. So I replace these 3 dots, and then I add a dot and call draw, which is a method that lives within the tile itself. Before I run this, I'll make sure that the tabulations are correct. So I'm just going to press Alt-Shift-F in VS Code, and that automatically fixes everything. Let's run this program. If we run this, great, we don't see any green color at all. However, we are not able to move the window around, and the reason why is because our window is not interactive. So I am forced to close the window manually after the program crashes and closing the program. What we need to do to create an interactive window is to go through every single event in the list of events of pygame, telling the program that we are accepting interactions with the window. We do this by using a for loop that goes through every single event in the list of events that pygame has, and we can access through the method get. If the event is of type pygame.quit, notice that quit is a constant, then we call pygame.quit, but this time as a method. That's it. If I run the program once more, this time I will be able to move the window around and the program is still running. It's time to implement the algorithm. Our algorithm will start by copying our template for tile row. This time we will replace these 3 dots for the series of actions that apply the specific rules of our algorithm. The main goal here is to calculate a value C. A value C that represents the return value of a function that consumes the tile. This function is going to be called map from a function. It is a higher order function. It means that besides taking the tile as an input, it will take another function that we will call fn0 for now. The value C will then become the tile's color that we're going to calculate by simply applying C 3 different times. One for red, one for green, and one for blue. The last thing we need to do is to make sure that we create these 2 helper functions and our program will be done. Let's start with the function fn0. This function will receive 2 elements or parameters that are both integers, and it will return an integer as well. The function will take the variable x and it's gonna apply the modulo operator with 256. Then we will add to it the equivalent but for the y-axis, modulo 256, and after the addition has been done, we will divide by 2. We are gonna return this value. Let's work on our higher order function. This function will be called map from fn, and it will receive the title and the function that we are gonna run or apply to that title. We're gonna create a variable name value, and we're gonna make it equal to the return of the function that sends the tile's position in X and the tile's position in Y. Once we have it, we return it. We're gonna return the integer version of this value. Now our values should already be integers. Let's see what happens if we just leave that out. Otherwise, we will do the casting. Let's run this program and let's see what happens. Success. You can see that our two-dimensional grid contains now a beautiful fractal that is represented by the modulo operations, but this time in 2 dimensions. Let's play with another function. At this point, the only thing we need to do is to define our functions. Let's create fn1 that receives the same parameters, and this one is going to use 2 local variables, xval for x value, because it would be rather confusing to keep everything in one single line. The purpose of each of these local variables is to calculate the sign of the variable x plus 1 and then multiply it by 127. We do the same, this time for the y-axis, still using the sign function. And then we can return the x value plus the y value divided by 2. This one should be y value. We're going to go to the call of the higher order function and we're going to change it from fn0 to fn1. We run it once more and there it is. For the first time, we have an interesting problem. It may seem that no matter if we add more tiles to the grid, let's prove it, the resolution of our animation doesn't really change. There is really not much improvement. So let's try with 4 and let's try with 48 by 48. So we have a screen that is made out of way more squares, and those squares are smaller. We are gonna introduce a new helper function, one that is gonna require the incorporation of a new hyperparameter as well. This one will be called the range x and y, and it will be defined as a scalar. In this case, I want the number 3. Let me show you how to use it. Here is my remap function. It receives a value that has to be transformed, the minimum value and the maximum value in the original scale, and the minimum value and the maximum value in the destination scale. And then it applies this formula. I'll give it to you as a challenge to digest this formula and see how it works. The conceptual part of it, which is the important part, is this. Suppose that I give you a scale that is from 0 to 10, and I give you the number 3. Suppose then that I give you a new scale that goes from 0 to 100. If from 0 to 10, the number 3 is at the 4th position, what percentage corresponds to the same value in a new scale from 0 to 100? You can probably guess that the value is 30. That is what this function is doing. And our goal is not to rescale between decimals or centesimals. It's to take the value of negative range to positive range. What is the same proportion 3? In a new value that goes between negative range and positive range. Let's apply this helper function. Rather than passing to the function from the higher order function here, as tile.x and tile.y, we need to calculate x and we need to calculate y. This one will be the remap function from the value tile.x that goes from 0 to to a screen at index 0. And I want to rescale it to a value that goes between negative range to positive range, passing through 0. I do the same thing, but this time for the y-axis. And it should take the second element of the screen, because that is the total number of pixels per height. Then I pass x and y instead of the tile attribute x and y. And now I can modify the function. From now on, we won't need to make these weird ad hoc effects that will help us fix the values between 0 and 255 every time. This time we can simply call the function that we want and then pass to it the variable of choice. The same goes for the y-axis. Now the newly calculated values that come out from this relationship will be defined between -1 to 1. So we need to use remap once more. If we don't, we'll just see a black screen because every pixel is defined between -1 and 1. So before we return the value, we are going to use remap to take that value from a scale that goes between 0 and -1 and 1. And we're going to transform those values between 0 and 255. Then we need to make sure that these values are integers, and then we can run the program. There it is. And now you can see that we start looking at something that looks a lot like certain types of pseudo-random noise. In fact, Perlin noise, which is one of the most famous forms of creating landscapes procedurally, Minecraft does that, use something called octaves, which are relationships between sine waves. Let's zoom out a little bit by adding values to the range. Let's add a 0 to the range. And we are zooming out. Now we can be a little more bold with the total dimensions of our screen. I'm going to make this 15 just for fun, and let's run it once more. Fantastic.